Welcome back. So we saw how the ideal gas result, one can go from the microcanonical to the canonical. Now we want to take another example, and that is of a set of classical harmonic oscillators. The Hamiltonian of the system was pi square over twice m plus half sum over m omega square qi square. This is a one-dimensional case. The generalization to higher dimensions is very trivial to do. So that when we did this in the microcanonical ensemble, we essentially made a change of variable where we had written that qi is qi prime divided by m omega, so that the Hamiltonian is I. So in this transform variable, the Hamiltonian is pi square over twice m plus half of sum over I m omega square qi prime square over m omega whole square, and that gives me sum over I pi square over twice m plus half sum over qi prime square over twice m. So the hypersurface, so essentially the hypersurface is given by twice me is sum over I pi square plus qi square, and you are looking at a hypersphere just as we had for an ideal gas, except that this is in a this is n-dimensional, so you're looking at a 2n-dimensional phase space. So please be careful in keeping count of the dimension of the phase space, because I've started with one-dimensional, I come up with 2n-dimensional, n coordinate and n momenta and n coordinate. The total number of microstates we calculated was h to the power n integral h of e less than equal to e dp1 to dpn dq1 to dqn, which in using the transform variable becomes 1 over m omega raised to the power n h less than equal to e dp1 to dpn, and then I have dq1 prime to dqn prime, and this is equivalent to the volume of the hypersphere in 2n-dimensional phase space. Now I know what this volume is. Please note that there is no n factorial here because these particles are distinguishable by their position. The mean position 1 over m omega raised to the power n 2 pi to the power n divided by gamma n plus 1. Remember that the general result for a volume of a hypersphere in d dimension was 2 pi d by 2 divided by gamma d by 2 plus 1 raised to the power r to the power d by 2, and in this case d is equal to 2n. I have twice me raised to the power n. So starting from this expression, I can define the n particle joint probability density rho n of p1 q1 p2 q2 pn qn as 1 over omega. So this is the joint probability density, and our interest lies in the single particle probability density rho 1 p1 q1 for one particle to be in a microstate defined by p1 q1, and this we do by integrating over P2 Q2, P3 Q3, Pn Qn, the other degrees of freedom. The answer we already know, we have done it in the last lecture, and I have rho 1 of, in terms of the number of microstates, the single particle partition probability density is given by 1 over h omega of En minus 1 n minus 1 divided by omega of E comma n. So using this expression for the total number of microstates for n particles with energy E, I can write down omega of En minus 1 n minus 1 is going to be 1 over h to the power n minus 1, 1 over m omega raised to the power n minus 1 twice pi raised to the power n minus 1 divided by gamma of n, and I have twice me, not so it has to be e of n minus 1 times raised to the power n minus 1. So the two ratios then becomes n minus 1 divided by omega of E comma n is 1 over h to the power n minus 1, 1 over m omega raised to the power n minus 1, 2 pi to the power n minus 1 divided by gamma of n, and I have twice me n minus 1 raised to the power n minus 1, 1 over, now we write down the expression for omega En, and that is going to be 1 over h to the power n, 1 over m omega raised to the power n, 2 pi to the power n, gamma of n plus 1, and I have twice me raised to the power n. Let's collect the terms, prefactors, and then we will write down En minus 1 is, so this is going to be h to the power n, h to the power n minus 1, m omega raised to the power n, m omega raised to the power n minus 1, gamma of n plus 1, gamma of n, then I have 2 pi raised to the power n minus 1 divided by 2 pi raised to the power n, I have twice me n minus 1 raised to the power n minus 1 divided by twice me raised to the power n. A lot of cancellations follow, and I have h, then this gives me over m omega, this cancels, this n cancels, I have 2 cancelling out, pi to the power n cancels with pi to the power n, I'll be left out with 1 over pi, gamma of n plus 1, gamma of n plus 1 is n factorial, gamma of n is n minus 1 factorial, so that I have n coming in the denominator, and then I have twice me n minus 1 raised to the power n minus 1 twice me raised to the power n. Now, if you look at the conservation of energy, then the total energy E is going to be sum over I pi square over twice m plus half m omega square I q, sorry, omega square qi square. And this I can split as the energy of the first particle, which is p1 square over twice m plus half m omega square q1 square plus sum over I is equal to 2 to n pi square over twice m plus half m omega square qi square. And this is the part which I identify as the energy of my n minus 1 oscillators, so that this becomes E of n minus 1, as we had done in the free particle case. So E of n minus 1 is then E minus p1 square over twice m minus half m omega square q1 square. Therefore, the ratio omega of En minus 1, n minus 1, omega of E comma n is going to be h over m omega n by pi. I'm going to have twice m E minus p1 square over twice m minus half m omega square q1 square divided by twice m e raised to the power n, and this one raised to the power n minus 1. Once again, let's rewrite this by taking one factor of 2me outside this bracket in the denominator. So this gives me h over m omega. Is this correct? Let's just see. Yeah, so this is not right because this is going to be m omega inverse. So this is m omega inverse. This is a mistake that I made. And I have m omega inverse, which essentially means that I have h by pi m omega times n divided by twice me, and I have, if I take the twice m inside the bracket, then essentially I have twice me minus p1 square minus m square omega square q1 square divided by twice me raised to the power n minus 1. A little simplification then gives me cancels out, h bar omega over, so I have the 2 pi takes care of h bar omega. I have h bar omega n over e, and this one I can simplify. 1 minus p1 square plus m omega square q1 square divided by twice me raised to the power n. Here I have again used the approximation, n minus 1 is going to be n. Now once again, you see the argument is that E is an extensive quantity, therefore the E energy scales with n, and I can approximate this bracketed expression as e to the power minus p1 square plus m omega square, m square omega square, I missed the m square in the above expression, q1 square divided by twice me. And this is being raised to the power n. So that this is h bar omega n by e. I have e to the power minus n by e times p1 square m square omega square q1 square divided by twice m. Now for a set of n oscillators, I know that E is equal to nkBT in one dimension. So if I now substitute this result, I have h bar omega, n by E is 1 by kBT, and then I have e to the power minus 1 over kBT, p1 square over twice m plus half m omega square q1 square. So that if you recall, rho of p1 q1 was 1 over h omega of en minus 1 n minus 1 divided by omega of e comma n, the ratio of these two quantities, and this becomes omega over 2 pi kBt e to the power minus 1 over kBt p1 square over twice m plus half m omega square q1 square. So this is exactly the canonical distribution of a single oscillator. We have done this in the class, and you are also invited to check this. So essentially, since I can choose any arbitrary oscillator, I mean I can choose the second oscillator, third oscillator, so P1, Q1 does not make any sense. I can replace this by writing rho 1 of PQ, the single particle density, as omega over twice pi kBt e to the power minus 1 over kBt P1 square over twice m plus half, no longer identified by the index, plus half m omega square q square. You can check the normalization of this. So very briefly, if for a single particle the Hamiltonian is given by P1 P square over twice m plus half m omega square q square, and the canonical partition function is z. Single particle partition function is q is going to be dp dq e to the power minus p square over 2m e to the power minus beta m omega square q square by 2. Both these integrals separate out and you have dp beta p square over twice m dq minus beta m omega square q square over 2. Their Gaussian integrals, ranges running from minus infinity to plus infinity, minus infinity to plus infinity. The first answer is square root of pi to m over beta, and the second answer is pi beta m omega square times 2. So that if you take everything common, simplify this, 2m pi by beta into 2 pi over beta m omega square. Mass cancels out and this is raised to the power half. We are going to have 2 pi over beta square omega square 2 pi whole square, and this is being raised to the power half, and the single particle partition function becomes twice pi over beta omega. So this is exactly the factor that you have, beta omega over twice pi, which is also the inverse of the normalization. So now in both the cases that we have looked at so far, essentially our microstates were continuous, in the sense they were not discrete in microstates, and we now want to take a look at a system where my microstates are discrete, and that essentially corresponds to a set of quantum oscillators. And here you have the energy eigenvalues, which are n plus half discrete, n plus half h bar omega, and when we did look at this system using the MicroCanonical approach, we said that the microstates are defined by the occupation numbers ni. Right? So the total energy was given by sum over I, ni plus half h bar omega, which is sum over I h bar omega times ni. So we can recast this by writing E over h bar omega was sum over ni I plus sum over I half, and this implied that sum over ni was E over h bar omega minus n by 2, and this sum we call it as m, and this is what we had the expression. So n particles, there were n quantum oscillators with a energy, with a total energy E. And this means that you have the set of numbers, integers m and n that we are looking at, and we said, look, this essentially translates to n minus to m balls or m particles and n boxes. How many possible ways of putting that? So n boxes means n minus 1 partitions, therefore the total number of objects possible was m plus n minus 1 because the two of them are fixed at the ends. So the total microstates that we obtained was m plus n minus 1. These are all possible permutations that have been considered, combinations, and therefore the double counting comes if you interchange the particles, nothing changes, and if you interchange the partitions, nothing changes. We had m factorial n minus 1 factorial. Now the idea is I want to determine the single particle density. So we had rho of n1, n2 was 1 over omega. Now from this I want to find out rho of n1. And it's the same procedure where we have to sum in order to get this single particle. So we'll call it rho 1 as before and rho n as this. In order to get this quantity, I have to sum over n2, n3, rho n of n1, n2. Right? You will come up with the same expression that we had before, except these are discrete microstates, so you do not need the h factor. So essentially rho 1 of n1 was going to be omega of e minus, so we will write down e n minus 1 with n minus 1 particle divided by e comma n. The h factor is not there, right? Because here the microstates are discrete, so they are in any case dimensionless number. Now if I have n minus 1 particles, that means E is going to be n1 plus half h bar omega minus sum over I ni plus half, plus ni plus half h bar omega. So that E over h bar omega is going to be n1 plus half, and this sum runs from I equal to 2 to n. So let's see, instead of writing E divided by h bar omega, I have E minus n1 plus half h bar omega is sum over, and then I have 1 over h bar omega is sum over ni plus sum over I equal to 2 to n half of that, and this sum is now 2 to n. So let's call this sum as m prime plus n minus 1 divided by 2. Then I have E over h bar omega minus n minus 1 by 2 is going to be n1 plus half plus m prime. So we somehow have to relate this with m. If I look at the left hand side, and I have n minus 2 plus half, and this one is minus n1 minus half is going to be your m prime, right? Then you see the half cancels out, and this is already, you have defined it as m, so that you have m minus n1 as m prime. So now what does this mean? That if I picked up one particular oscillator, then essentially you are left out with m minus n1 particles and n minus 1 boxes. Originally, when you were considering n particles, you had n boxes and m particles. Now if you pick up the n1 oscillator, this occupation number, and you want to know the probability density rho 1 of n1, then essentially you're looking at m minus n1 particle and n1 boxes, so that you have essentially n minus 2 partitions. So therefore you have m minus n1, the total number of objects is n minus 2 factorial divided by n minus 2 factorial, and then you have m minus n1 factorial. So that this is omega n minus 1 in shorthand notation, and therefore rho 1 of n1 is going to be m minus, so let's just write it down, m plus n minus n1 minus 2 factorial divided by n minus 2 factorial m minus n1 factorial, and then we had the original, which was m plus n minus 1 factorial, and we had m factorial n minus 1 factorial. Now let's group the terms together so that it is easier to see what we are going to get. M plus n minus n1 minus 2 factorial divided by m plus n minus 1 factorial, and then I have m factorial m minus n1 factorial, and then I have n1 factorial n minus 2 factorial. The most trivial of this is the last term, which is going to be n minus 1 and is going to be approximated by n. Let's look at this. Let's look at the denominator first. I have m plus n minus 1, m plus n minus 2, all the way up to m plus n minus n1 minus 1, and then I have m plus n minus n1 minus 2 factorial. The numerator is m plus n minus n1 minus 2 factorial. This term is m minus 1, m minus 2, all the way up to m minus n1 plus 1, and then I have m minus n1 factorial divided by m minus n1 factorial, and of course I have the last term, which is n. A simplification would mean that this and this cancels out, and this and this cancels out, so that I have m minus 1, m minus 2, m minus n1 plus 1 divided by m plus n minus 1, m plus n minus 2, and all the way we are going to m plus n minus n1 minus 1. So we are almost there. You have to just hold on a little bit more, and then I have n. Now clearly in the thermodynamic limit, what I can do over here is there are n1 such terms, so that this is going to be m to the power n1, and this is going to be m plus n. There are n plus 1 such terms, is going to be n plus 1 times n. So that rho 1 of n1 is going to be n divided by m plus n times m over m plus n raised to the power n1. Now I can recast this as, well, here this becomes 1 over 1 plus m over n, and this is 1 over 1 plus n over m. raised to the power n1. Now, if you go back to the lecture on this quantum oscillator treated microcanonically, you will see that 1 plus n over m was e to the power h bar omega over kBt. So that this factor is e to the power minus n1 h bar omega kBt. And from this, I can write down m by n as e to the power h bar omega over kBt minus 1 inverse. So that I have rho of n1 is 1 plus, okay, we have to do one more step. I am interested in now 1 plus m over n, which is going to be 1 plus e to the power, not e to the power, 1 divided by e to the power h bar omega over kBt minus 1. And if I do this, it's going to be e to the power h bar omega over kBt minus 1. You see, the minus 1 in the numerator is going to cancel with this one. You will be left out with h bar omega over kBt, which is nothing but 1 minus h bar omega over kBt. And therefore, rho 1 of n1 is going to be 1 over 1 minus h bar omega over kBt e to the power minus n1 h bar omega over kBt. And this is essentially the probability that a particle or an oscillator is in the nth quantum level. Here, of course, n1 is nothing special, so one can write down rho 1 of n as 1 over 1 minus h bar omega over kBt e to the power minus n h bar omega over kBt. So now with this expression, we can take it a little bit further. Let's say I have rho 1 of n is going to be 1 over, I want to multiply by e to the power minus beta h bar omega by 2 and divided by, or let's say plus and e to the power beta h bar omega by 2, 1 minus h bar omega over kBt, and this becomes minus n h bar omega over kBt. You immediately see that this results in the following simplification. The numerator now I can write down minus beta, beta is kBt inverse, n plus half h bar omega times e to the power minus beta h bar omega over 2 divided by 1 minus h bar omega over kBt. So that I have e to the power minus beta epsilon n, and then I have e to the power minus beta h bar omega by 2 divided by 1 minus beta h bar omega. If you recall, this is a single particle canonical partition function for a harmonic oscillator. We have done it explicitly. So essentially here also we explicitly showed that you can go from the microcanonical to the canonical probability density.